reactant is in gaseous phase, product also is gaseous phase. If the reactant is solid phase, the product will also in solid phase. For pure solids and liquids, concentration is constant, that is unity. Consider a general reaction represented by a balanced equation. The products are spontaneously converted to reactants, that is from backward reaction at this instant. This continues till equilibrium is reached. Hello everyone, this is Harshita Bhavasar from Vidhyaashram, PU College, Temple of Excellence. Today, I am going to start session 3 from the chapter Chemical Equilibrium. In the last session, we have discussed about rate or velocity of a reaction and law of mass action. These two contents we have discussed in the previous session. In this session, we will discuss about homogeneous equilibria, heterogeneous equilibria and applications of equilibrium constant. First, we will see what is homogeneous equilibria. Homo means same or same phase, like that we have to understand. What do you mean by homogeneous equilibrium is, in homogeneous system, all the reactants and products are in same phase. If the reactant is in gaseous phase, product also is in gaseous phase. If the reactant is solid phase, the product will also in solid phase. That is what the reactant and product, if it is in the same phase, that system will be considered as homogeneous system. We will see one example. See here, nitrogen is in gaseous phase and also hydrogen is in gaseous phase. What is the ammonia is getting to formed, that is also in gaseous phase. Then what is the equilibrium constant of different concentrations, that is Kc. This is ammonia and here nitrogen and hydrogen and different pressures, partial pressures, ammonia, partial pressure of nitrogen and partial pressure of hydrogen. Overall equilibrium constant in gaseous system. Okay, this overall reactant and product are in gaseous system. So, equilibrium constant will also in gaseous system. Then relationship between Kp and Kc. Between equilibrium constant of partial pressure and equilibrium constant of different concentrations. What is the relation between them? PV equal to nRT, which is an ideal gas equation. Okay. So, P equal to N by V into RT. What they are doing? P equal to N by V, what is there? It will be represented by C, R into T. Okay. Here, consider a general reaction. This is A, small a, what all the small letters are given, that all the moles of a reactants and products. A plus B gives rise to C plus D. At partial pressure, see here, pressure of C and this is mole, pressure of D and this is also mole. This is product, this is reactant. What will happen? RT, that is gas constant and temperature, they have written like this and moles they are adding here. It will become C into D, A into D with their moles. RT has taken common C plus D minus A plus B because they have taken denominator to numerator. That time what will happen? This positive sign will become negative. See here, equilibrium constant at partial pressure, that is Kp equal to Kc, RT, C plus D minus A plus B. This whole thing they have represented as Kc. Okay. What will happen? Kp equal to Kc, RT, number of moles. These are all number of moles, right? So, delta is difference in number of moles. This is the expression which shows the relationship between Kp equal to Kc or Kp and Kc. Kp and Kc are related as Kp equal to Kc into RT to the power delta n, where R is gas constant, T is temperature on absolute scale, delta n is number of moles of gaseous product minus number of moles of gaseous reactants. How it will be calculated? We will see here. Example, nitrogen and oxygen treating with each other and forming nitrogen oxide. You have to calculate the delta n. How you will see? What is the formula here? Number of moles of gaseous products minus number of moles of gaseous reactants. So, delta n equal to here 2 moles from product, 1 plus 1 Okay, 2 moles from reactant. So what will happen? 2 minus 2, 0. Then Kp equal to Kc into RT to the power 0. That shows Kp equal to Kc. Okay. Another example we'll see. Nitrogen and hydrogen is treating with, will give rise to ammonia. See here, overall 2 moles from product, and here 1 plus 3 equal to 4. 2 minus 4 minus 2 will form. So Kp equal to Kc into RT minus 2, or Kp is lesser than Kc. If this is in negative sign, so Kp is less than Kc. We'll see another example. PCl5 gives rise to PCl3 plus Cl2. What is product? Overall 1 and 1, 2 will happen. Here 1, 2 minus 1, 1 equal to 1. So Kp equal to Kc, RT to the power 1. So Kp is greater than Kc. Here what you have to understand, all the three conditions you have seen, Kp equal to Kc and Kp is lesser than Kc, as well as Kp is greater than Kc also. If it is positive, it will be greater. If it is negative, it will be lesser. If it is 0, it should be equivalent to each other. These are the example which show the relation and how it has to be predicted between Kp and Kc. Next, equilibrium constant in gaseous state. For the reaction, hydrogen and iodine, it will form hydrogen iodide. So, same formula we have to use. PV equal to nRT, P equal to N by V into RT, P equal to CRT. What they are showing here? Kp equal to PHI to the power 2R square, PH2 into PI2 equal to Hi in gaseous state into RT. This RT you are representing, this 2 also you are representing here. And the individual H2 into RT, I2 into RT. So what will happen? Hi divided by, here I should be there, Hi divided by H2 into I2 will form Kc with different concentrations. In this example, Kp equal to Kc, that is both equilibrium constants are equal. See here, both equilibrium constants are equal, 2 and 2. It is showing Kp equal to Kc. Next, for the reaction N2 plus 3H2, what will happen? 2 moles of ammonia. Same mathematics you have to use here, ammonia in the product and individual reactant. Here also you have to implement the reaction, that P equal to CRT. RT they have implemented. What will happen? Ammonia in gaseous state. In RT minus 2 will happen. This is individual reactant N2H2. Kc into RT minus 2 to the power minus 2 will happen. Okay. Here also PCl5 will decompose into PCl3 and Cl2. Everything is same. Kc into RT. Okay. What are the units of equilibrium constant? Unit of Kc, mole per liter into the power delta N, and unit of Kp, unit of pressure to the power delta N. This is different concentration. This is different partial pressures. Next one is heterogeneous equilibrium. We know now what is homogeneous equilibrium. In the homogeneous system, the reactants and the products will be in the same phase. Okay. Here, in this reactants and products not in the same phase, this will be in different phases. We'll see one of the example. Calcium carbonate will be in the solid phase. When it is getting to decompose, calcium oxide and carbon dioxide will form. See here, calcium oxide is also in solid phase, but carbon dioxide will be in gaseous phase. This reaction will shows, or this system will shows the heterogeneous equilibrium. Here, Kc equal to calcium oxide into carbon dioxide, the reactants. These are the products and this is reactant, calcium carbonate. Concentration of solids are constant. Kc equal to carbon dioxide in gaseous phase, or Kp equal to PCO2. This is in different pressure, no? That's why. In the reaction, another reaction, this is silver oxide plus nitric acid will form silver nitrate and water. See here, this is also in solid, this is in aqueous, this is again in aqueous in solid. What will happen? Kc equal to AgNO3 by HNO3. For pure solids and liquids, concentration is constant, that is unity. Okay, here also power 2 is there, here also power 2 will be applied. Next, applications of equilibrium constant. What all the applications by equilibrium constant, how it will be useful for the reaction. Okay. The magnitude of equilibrium constant is a measure of extent to which reaction will occur. What is the use of equilibrium constant? This will help in the measuring of the extent which reaction will occur, whether it's a forward reaction, whether it's a backward reaction. So it will show, and till what extent the reaction will happen also, the equilibrium constant will show. Next, predicts the direction of the reaction. Like as I said, forward or backward reaction also it will show. It is used to calculate the equilibrium concentrations. Kc is nothing but equilibrium constant and different concentrations. That means it shows or it calculates the equilibrium concentrations also. So these are the main three applications of equilibrium constant, and we'll see one by one with some of the examples. First, predicting the extent of a reaction. If Kc is very large, much greater than 1, then forward reaction will proceed nearly to completion. That is, formation of product is favored. Once again, if Kc is very large, means equilibrium constant of concentrations, if very large or much greater than 1, forward reaction will proceed till the product will be formed. Okay. See here, methane is treating with chlorine. Methyl chloride will happen with hydrochloric acid. What you have to see, product by reactants equal to 1.2 into 10 to the power of 18 at 298 Kelvin. Okay. Till the product is formed, and it is a forward reaction. Forward reaction proceeds nearly to completion at 298 Kelvin. Okay. And if Kc is quite small, if it is quite small, less than 1, then forward reaction rarely occurs. Most of the reactants remain unreactant. This will also shows or proceeds forward reaction, but the sum of the reactants will not react, it will be remained as such. See here, nitrogen and oxygen, nitrogen oxide will form. Here the reactants, here the product, 4.5 into 10 to the power of minus 31 at 298 Kelvin. The reaction does not take place at all at 298 Kelvin, means the sum of the reactant will have been unremained or unreacted. Next, prediction of direction of a chemical change. Consider a general reaction represented by a balanced equation. See, by the balanced equation, moles, small letter will shows the moles, and here reactants A plus B, and this is product. Reaction quotient is defined as Q. What all the quotient will be designated by Q? This one you know, product by concentration of product by concentration of reactant. When molar concentrations are instantaneously molar concentrations at any given instant, it may be noted that reaction quotient has the same form as the expression for K. Means this Q will be equivalent to K, but it contains the actual concentrations at a given instant instead of equilibrium concentrations. At that given instant will show Q, the equilibrium concentrations will shown by K. The value of Q changes as the reaction proceeds and approaches the K. Equilibrium achieved when Q equal to K. When the reaction is keep on proceeding, Q will be keep on changing till it reaches the K, that is equilibrium constant. When the equilibrium has been reached, that instant equilibrium and the total equilibrium constant will become same. Okay, Q equal to K. Suppose that at a certain instant Q is greater than K. If it is in this case, instant equilibrium, the total constant is at the different phase, then from first reaction, delta G is greater than 0 and the forward reaction is non-spontaneous. Gibbs free energy will be used here. So, if delta G is greater than 0, the forward reaction will be non-spontaneous. The products are spontaneously converted to reactants, that is from backward reaction at this instant. This continues till equilibrium is reached. the non-spontaneous reaction will be proceeded in backward reaction till the equilibrium is reached. If Q is lesser than K, then delta G is also less than 0 and the reactants are spontaneously converted to products, that is in the forward reaction only. If Q is lesser than K, it will proceed spontaneously. If Q is greater than K, it will not proceed with spontaneously. It has to be converted into backward reaction to form the product and to reach the equilibrium. If the Q is lesser than K, the delta G is also lesser than 0, it will spontaneously react to form product and also the forward reaction will occur to reach the equilibrium. If Q is equal to K, then the system has already attained the equilibrium and no net change takes place in either direction. If Q is equal to K, that is instant equilibrium and total equilibrium constant, if it is in the same phase, no changes will be seen and also no direction of reaction will takes place in any way, either in the forward or in the backward, because already instant equilibrium and also total equilibrium constant is in the same phase. See another, all the cases we have written in concisely. If QC is lesser than KC, forward reaction is favored until equilibrium is established. If QC equal to KC, reaction is at equilibrium. If QC is greater than KC, backward reaction is favored until equilibrium is established. These three cases only we have seen now with different examples. See here, reactants and products showing forward. If QC is lesser than KC, forward direction. If QC and KC is at equal stage, reactants and products are at equilibrium. If QC is greater than KC, it is giving in backward direction to reach equilibrium. These are the three cases with the diagrams. Next one, calculating equilibrium concentration. In case of a problem in which we know the initial concentration but do not know any of the equilibrium concentrations, the following steps shall be followed. In any problem or any case of problem, we know initial concentration but we doesn't know any equilibrium concentration, then what we have to do? Write a balanced equation for the reaction. You have to write the balanced equation. Under the balanced equation, make a table that lists for each substance involved in the reaction. Like you know that how to balance the reaction, then you will interchange the moles. Like that you have to specify each and every concentration, each and every reactants you have used also. Initial concentration, the change in concentration on going to equilibrium and the equilibrium constant. These are the three steps you have to note it down below the balanced equation. In constructing the table, define X as the concentration of one of the substance that reacts on going to equilibrium. Then use the stoichiometry of the reaction to determine the concentrations of the other substances in terms of X. Which you doesn't know the concentration, you have to define X and that X should be calculated by a known form of concentration by using stoichiometric method. Next one, substitute the equilibrium concentrations into the equilibrium equation for the reaction and solve for X. By correlating with known and unknown concentration, you have to calculate. If you are to solve a quadratic equation, choose the mathematical solution that makes chemical sense. You have to use your quadratic equation which will use in the mathematical expressions and you will get to know the unknown concentration. Next, calculate the equilibrium concentrations from the calculated value of X. Now your X will be get to know. Check your results by substituting them into equilibrium equation. What all the X, that is unknown concentration, you will get to know, that you have to implement in the equilibrium constant. Okay, this is how equilibrium concentration can be predicted. Degree of dissociation of reactant. Alpha, you know, degree of dissociation, that will be equal to number of moles of reactant dissociated by total number of moles of reactants taken. How much? The number of reactant dissociated by total number of reactants you have been taken. By that, you will get to know degree of dissociation. Okay. This is how the homogeneous and heterogeneous equilibrium and also the relationship between Kp and Kc and also applications of equilibrium constant by predicting the direction, by predicting the number of moles, everything will be used. So, in the next session, you will understand factors affecting equilibrium and ionic equilibrium. These are the two contents which we will discuss in the next session. I hope you have understood completely whatever I have taught today. We'll meet in the next session. Thank you.